Okay, let's get into it. If you've ever had a COVID-19 test, you've probably had that thought. After the uncomfortable swab, what in the world happens next? You get a result back, sure, but that in-between part, it's a pretty amazing piece of molecular detective work. So today, we're going to pull back the curtain on the PCR test. Right? It's a great question. Your sample doesn't just sit there. It goes on this wild, high-tech journey. It gets to the lab, gets logged in, and then the real science kicks off. So what are the lab techs actually doing to find a teeny tiny microscopic virus in your sample? The easiest way to wrap our heads around this is to follow one single sample. We're going to trace its path from the moment it hits the lab all the way to that final result. Think of it like a story with a clear beginning, middle, and end. All right, first things first. The lab isn't really looking for the whole virus particle. Not exactly. They're hunting for its genetic fingerprint. So the very first, and maybe the most crucial step, is to pull that genetic material out from everything else that's in the sample. This whole extraction thing breaks down into 3 main steps. So after your sample's collected, the lab techs use this special kit to basically crack open any virus particles and let their genetic code out. The whole goal here is to get a really clean, pure sample of just the virus's RNA and get rid of all the other junk, human cells, bacteria, all that noise. So what even is RNA? Well, just think of it as the virus's personal instruction manual. It's the unique genetic blueprint. Every virus has a totally distinct RNA sequence, and that is the specific clue our test is designed to find. Okay, so how does the test actually find that one specific string of RNA? Well, the secret is in this pre-made master mix that gets added to your sample. And this isn't just some random chemical soup, oh no. It's more like a highly specialized genetic search party, where every single ingredient has a very specific job to do. So let's meet the members of this search party. First, you've got the primers. These are like tiny trackers that are programmed to find and latch onto a very specific part of the virus's RNA. Then you have the probes. Think of these as glowing tags that attach right alongside the primers. And finally, you've got something called an internal control, which is basically a built-in quality check to make sure the test itself is running the way it's supposed to. And when I say precise, I mean incredibly precise. There's a quote from the test manufacturer's own manual that says the trackers and tags are designed to be an exact match for the COVID-19 virus's genetic code. They won't grab onto the flu or a common cold or anything else. They are looking for one target and one target only. But here's the thing. Even if the virus's RNA is in there, there might only be a tiny, tiny amount, way too small to see. So what's the solution? We need to make copies, a lot of copies, billions actually. And to do that, the sample goes into this amazing machine that works like a molecular photocopier. So the machine starts this series of rapid-fire temperature changes. First, it cranks the heat all the way up to 95 degrees Celsius. This intense heat causes the 2 strands of the RNA's genetic code to separate, or unzip. This basically gets them ready to be copied. Next, the temperature drops down to 60 degrees. Now, this is the perfect temperature for our little trackers, the primers, to swim around, find their specific target on that unzipped viral RNA, and lock on. Of course, if there's no viral RNA in the sample, the trackers just float around with nothing to attach to. Then the temperature bumps up just a bit to 72 degrees. This is the signal for another ingredient, an enzyme, to get to work. It starts copying the exact section of RNA that's been marked off by our trackers. And boom, just like that, we've made a perfect duplicate of the virus's genetic signature. Now, here is the truly amazing part. The machine doesn't just do this once. It repeats that 3-step cycle of unzipping, tracking, and copying 50 times. And each cycle doubles the number of copies. So you go from 1 copy to 2, then 4, then 8, 16, and this exponential growth turns a single piece of RNA into billions of identical copies. It's incredible. Okay, making billions of copies is awesome. But how does that actually turn into a result we can read? How do we know if the sample is positive? Well, this is where those glowing tags, the probes, finally get their moment to shine. It's actually a really clever system. The test uses 2 different colors of fluorescent dye. The probe that's designed to stick to the COVID-19 RNA is tagged with a dye called FAM, and it glows green. But the probe before the internal control, remember, our quality check, is tagged with a different dye, HEX, which glows yellow. So get this. Every single time a copy of the RNA is made, one of those glowing tags gets released, and it creates a tiny little flash of light. Now, when you have billions of copies being made, all those tiny flashes add up to a bright, steady glow. The PCR machine is actually a super sensitive light detector, and it's constantly measuring how bright that light is getting. So, at the very end of those 50 cycles, the machine has a final reading for each sample. It knows exactly how much green light and how much yellow light is glowing inside that tiny tube. And that data is what a lab technician uses to make the final call. And the logic here is actually super straightforward. If the machine sees a green glow and a yellow glow, that means the virus was there and the test ran just fine. That's a positive result. If there's no green glow, but there is yellow glow, it means the virus wasn't there, but the test still worked perfectly. That's your negative. And if nothing glows, no green, no yellow, the test is invalid. Something just didn't work right. See, this is why that yellow glow is so important. That internal control is our guarantee. It's our proof that the test reaction actually happened. Seeing that yellow light gives us confidence in the result. Without it, even a negative is untrustworthy, because for all we know, the whole test just failed to run. It's a brilliant, simple quality check built right into the process. So when you put this all together, what's the big takeaway from this whole journey? Well, it's that the PCR test is an unbelievably precise and specific tool for diagnosis. I mean, to make sure this thing doesn't get confused, the manufacturer tested it against a whole list of other viruses. It doesn't react with other coronaviruses like the original SARS or MERS. It doesn't react with herpes, varicella zoster, that's chickenpox, or Epstein-Barr. This analytical specificity is really what makes the test so powerful and reliable. Honestly, the best way to think about it is this. The whole test, the primers, the probes, it's like a unique key that has been perfectly engineered to fit only one very specific genetic lock, the lock of the COVID-19 virus. If that lock isn't in your sample, the key has nothing to open, no copies are made, and the test comes back negative. Simple as that. And that leaves us with a pretty fascinating thought, doesn't it? This technology, this ability to find a specific genetic fingerprint, it isn't just for COVID-19. It can be tweaked to find almost anything, from other viruses and bacteria to the genetic markers for things like cancer. It's such a powerful tool, and it really makes you wonder, now that we can do this, what are we going to find next?